As we mentioned earlier, virus has coating protein forming its protective shell, right? And in addition to that, the virus also has some key enzymes like integrase or protease or transcriptase. And so one way is to indirectly detect the activity of these enzymes as a way to detect the presence of the virus. But as you may guess, it's similar to the cytopathic effects that we just talked about. They are non-specific because many viruses, different strains, can have the enzymes of the similar activity, and so they will show very similar phenotyping or detection. So we cannot differentiate them. Another way is directly and focusing on the viral coating protein. And before we get to the protein detection, I think it's very useful to refresh our knowledge on the immunity against the virus. So once the virus gets into the body and gets into the cell, it will start to make new copies of itself, making new viruses. And this virus will release into the extracellular space. And some of these new viruses will be taken up by APC, or antigen-presenting cells, a part of our immune system. What APC does, it will chop up the viral proteins into small peptides, small pieces of viral protein, and are called viral peptide. And they are the antigens. And so the APC will present the viral peptide on its surface through a specific receptor. And we know this peptide belongs to the virus. And so the immune system uses the peptide as a fingerprint for a specific virus. And what happens next is that in the immune system, there are T cells and there are B cells, and we have large pool of them with a huge diversity of receptors. And some of these cells whose receptor will happen to recognize the presented viral peptide will be activated. And the activated B cell will go on to start to make antibodies against the peptide. And this antibody can specifically recognize the peptide. And so the viral protein that bears this peptide, and through sensing the peptide, it will be able to tell the presence of the virus. And some of the B cells will keep going and mature into so-called plasma cells that will produce a huge amount of antibody in a later phase of the immune response to eliminate the virus. So now we have the virus, and we have the antibody against the virus. And so the antibody is a tool that we can then use to detect the virus. And there's two ways to use it. And the first way is, just to directly detect the viral coating protein by using these antibodies. The other way is a little bit indirect. It goes in two steps. So first, we let the immune system to detect the viral protein through the normal immune response. And then we test if the blood of the people that we want to test has the antibody that can specifically recognize the virus. And this will be the sign that this person has been exposed to the virus. Regardless of direct or indirect protein detection method, the protein detection usually takes the form of a method called ELISA, which stands for enzyme-linked immunosorbent assay. In the indirect ELISA assay, so the antibody which recognizes the viral protein is first absorbed onto the bottom of the well. Then we add in the sample, which may contain the virus. So if the virus is there, it will be bound by these antibodies. And then we wash and add in the second antibody, which also recognizes the same viral protein. And if the virus is there, this antibody will be bound and stay in the well. If the virus is not there, the secondary antibody will be washed away and will not be present in the well. And then we add in a substrate. And if the secondary antibody is there, the enzyme that linked to it will convert the substrate to a dye, so we'll be able to see it. as shown here. So this is like a real elastic IC, while in the wells and the stars showing the yellow color, there's the antigen that we want to detect. And the higher antigen level, the higher the brighter the dye we will be able to see. Another form of ELISA is called sandwich ELISA, in which case the targeted protein or the sample is first added to the well and is absorbed onto the bottom. And then the antibody is added into it, which will recognize the antigens. And then the secondary antibody will recognize the first antibody. And so if the antigen where the virus is present, the first antibody, and so the second antibody will stay in the well, and enzyme then linked to the second antibody will be present, and it will convert the substrate to a dye. And if the virus is not there, the first antibody will be washed away, and so there will be no secondary antibody and no substrate conversion to dye and no color. It works in a very similar way. So, I mean, those two methods are for protein detections. And if you want to detect the serological antibody or the antibody that present in a patient's blood, we just have to swap the sample and antibody. We can add in the known viral antigen and to test whether the patient blood contains the antibody against this antigen or not. And usually, in terms of protein detections, we would like to do an indirect way to detect the antibody rather than the viral protein, because antibody can be found in the patient blood, which is easily to be collected, and it usually is present in a much larger quantity compared to the viral proteins, and so they are easier to detect. So this forms the basis of some of the in-home 5 minutes tests. And those serological tests looks like this, a little plastic strip, and with input hole right here. And so the person who wants to do the test would drain a little bit of fingertip blood and add it to here, which is the sample pad in these schematics. And the blood will be attracted to the absorption pad placed on the other side of the strip. So blood will keep flowing in a laminar way from left-hand side to the right-hand side. And so the antibody then in the blood will also be driven by this flow. And so the antibody will first encounter, right here we have the COVID-19 antigen conjugate to the gold nanoparticle. If the antibody can recognize this antigen, it will bind to the antigen and form antibody-antigen nanoparticle 3-body pieces. And these 3 things will move together. And right here we have a line that will trap the IgM antibody. And in the second line, it will trap the IgG antibody. The IgM and IgG are just 2 forms of antibodies that we have in our blood. And then the rest of the antibodies will be trapped by the third line, which is a control line. And so the gold nanoparticle will give us a color, looks like the pink thing in the strip. And if we have the COVID-19 antibody in the blood, then the first line that attracts the IgM antibody will be able to attract those golden nanoparticles to the line, and so the first line will start to show pink color. And in a similar way, if we have the IgG antibody that can recognize the COVID-19 antigen, then the golden nanoparticle will be bound to the second line, and it will show as a pink line here. And if the person has both IgG and IgM antibody, then the both lines will be shown pink color. And this is how this fast serological test works. But there is a caveat of using this method. As we mentioned, the antibody generation is a result of very complicated immune response. And so it takes time. From the time of infection to the time when the person starts to show some symptoms, it can take several days or even a week. And then from the time the person starts to show like symptoms like fever, um, to the time when the IgM antibody to reach the level of detection, it will take another few days. So in total, it may take up to 2 weeks from the time of infection to the time of we can find detectable level of antibodies in the blood. The IgM is earlier. It starts to show up still during the active infection. IgG comes even much later. It's usually considered as an indicator for past exposure to antigen, and so it can cause a big problem because we know that asymptomatic carriers can still be highly contagious. They may still be spreading virus, even though their serological test can turn to be inactive for when they were in the incubation period. So we've discussed several different way of testing the viruses, and some of them are not very specific to the strain of the virus, and some, like the viral protein detection method, is a method that has a delay. And in order to quickly track the active virus spreading, we need to have a method that can detect the virus at this early stage. And this is something that we're going to talk about in the next section, the detection based on the viral genetic materials.